Hello, everybody. Um, Welcome to online section of tissue engineering lecture. Um, we are gonna continue with the scaffold fabrication techniques. Um, so we had gone through solvent casting and particulate leaching in our previous lecture, melt molding, gas forming, and freeze drying. Mainly these protocols, these processes are either used by individually or they are combined and used together to manufacture useful scaffolds. And as you remember in the beginning of the lecture, we had mentioned the important characteristics of the scaffolds. So please um, go through these features when you study individual manufacturing technique. So all of the target is to reach these specific features that we have mentioned previously. Now we're gonna continue with the five fibrous based the fibrous scaffolds, okay, and how we manufacture these fibrous scaffolds, and why those fibrous scaffolds are important in tissue engineering. So, so as you see in the image, um, scaffolds that are serving fresh surface area for cells to attach. As you see here, fibrous structures enables higher surface area for cellular adhesion. And if you consider the natural tissue structures in many tissues, they're all composed of nanofibers or microfibers. Okay, so the reason of those is to enabling higher mechanical strength to tissues and also serving high surface area for cellular adhesion. So cells in three-dimensional structures are getting interacted with the surface of the fibers. So higher surface area by enabling with the nanofibrous structures would be helping more cell adhesion in three-dimensional structure. And another important thing is cells are tend to attach to the structure of the scaffold in multi-dimensional structure, as you see on the very right downside image. Okay, in three-dimensional structure, they're attached to the fibers. So cellular interaction with the extracellular matrix is a dynamic and a demanding process. So this contact issue is not just for cellular adhesion requirement, it is also for uh, intersite cellular processes. So cells are demanding this adhesion to be alive and to manufacture their own tissues. So as you remember, the scaffold function is temporary and it's gonna be degraded after a while and replaced by an original tissue. So to be able to replace it by an original tissue, cells require to manufacture their own tissue, right? So this is important uh, for enabling cells in three-dimensional structure uh, adhesion support. And membrane-bound receptors are constantly recycled and renewed to bind to the matrix. In, as you see here, the fibrous, nanofibrous structures, scaffolds, they're also porous, and those pores are the same time allows nutrition and oxygen transport in the scaffold. That is another reason why fibrous scaffolds are preferred in tissue engineering applications. So there are a lot of scientific publications, review articles, uh, continuously being published, and this one you see in the publish after increased nanofibrous uh, attention in tissue engineering science in 2007, and basically explaining the nanotechnologically manufactured fibers in biomedical applications. There are currently more review articles discussing many sort of applications of nanofibers in tissue engineering. So nanofabrication techniques mainly being used in tissue engineering applications are electrospinning and self-assembly. There's also a fiber bonding technique, could be related with electrospinning. We're gonna see that as well in the manufacturing techniques. So these self-assembly studies initiated the in 2005 by Dr. Zhang in Harvard University. So in this studies, they had manufactured a RADA 16 amino acid, including RADA self-assembled nanofibrous structure. The as RADA um, each letter represents an amino acid. In RADA, R representing arginine, A alanine, D aspartic acid, and A alanine. So repeated of these RADA unit 4 times includes the 16 amino acids long of peptide. And this peptide is used in many applications so far. And this peptide specifically self-assemble and creates nanofibrous base hydrogels. So it's not only creating a nanofiber, but also it develops a gellus three-dimensional structure, and which is very important to be used, especially in soft tissue engineering applications. So in this specific paper, they used a neural regeneration process and presented successful results. So in the assembly, you see the molecular model of the RADA amino acids, and RADA molecules undergo self-assembly to form well-ordered nanofibrous with the hydrophobic alanine sandwich inside the hydrophilic residues on the outside. So obviously, if you prepare a water-based solution by using these hydrophobic hydrophilic amino acid containing peptide sequences, what happens is you're gonna be seeing the hydrophobic content is gonna be staying away from water, and hydrophilic content is gonna be turning towards water. So these hydrophobic hydrophilic interactions creates gellus formation, and that callus three-dimensional structure is being used as a bioactive scaffold option in tissue engineering.